Welcome back, everyone. I hope you all enjoyed the three first sessions. The energy and insight so far has been fantastic. So my name is Villanueva, and I'm honored to be your Master of Ceremonies for this next part. I'm eager to dive into our next topic, SDV by SDN, end-to-end approach to streamline deterministic application, presented by José Villanueva, as known as our expert in vehicle network with over 20 years of experience who have actively contributed to our community, having served as chair of our IEEE in 2016 and also a chair of Open Alliance in 2019 to 2020. This year also has been appointed as chair of our events and also hosted by Ampere here in Toulouse. Joining him, Ricardo Gonzalez de Oliveira. Ricardo is a control and automation engineer specializing in distributed safety critical systems. He currently works at Bosch on innovation projects focusing on next generation in vehicle networks, having previously worked on EE architecture for highly autonomous driving projects. Gentlemen, the stage is yours.
Thank you, Reda. So SDV by SDN, an end-to-end approach to a streamlined deterministic application on Ethernet-based IVN. So what is all of this about, SDN in the automotive? This is what we are going to try to explain today. So we'll start with two parts about the needs of the automotive automaker and a simple use case to know why those needs are necessary. Then this part will be presented by Ampere, and then Ricardo will take the lead to present how this can happen in automotive. So let's go started. SDN. What is SDN? The art of managing network configuration and engineering. Without SDN, everything in the vehicle is predefined. Applications came with requirements: latency, bandwidth, jitter. And we have some resources in the network, some physical resources. We have 100 megabit links, gigabit links. How to make all this work? So what we do in automotive is run simulations and validate the result of those simulations until we found a match between the needs and the network resources. And when we have found this match, everybody is happy, and we can deploy this network configuration in the network. But what happens if the network configuration, what happens if the needs changes? We need to run this process all again, and this is quite complex. So IT industry has found a solution to solve this problem. And this solution is what we call software-defined networking. With software-defined networking, we introduce, the IT has introduced a concept which is the SDN controller. The SDN controller understands the needs of the application dynamically, match these applications with available resources, and deploys the network configuration dynamically through SDN agents. When doing that, we are capable of servicing the new application needs and meeting the QoS requirements. And this is what IT industry has managed to do. So the question here today is, can we apply this mechanism to automotive? So yesterday was a very interesting discussion in the panel. So no, this cannot be applied. And yeah, we are completely right. Today we are deploying a static configuration mainly because we have a lot of constraints in the automotive. So here I will say that perhaps the answer is not a big no, but a yes, careful yes. Why? Because we have limited embedded resources, strict latency bounds, functional safety requirements as cybersecurity challenges. But if we manage to create an automotive SDN standard that cope with these mentioned constraints and makes the configuration simpler for the automakers and the tier ones, there will be a good benefit, a very big benefit, because we need to be faster on the way we configure today the networks. So it was said in our keynote, the idea to have standards needs to come from the needs. If there is not a need, we cannot make a standard. So here, we'll try to showcase what are the needs. So I already said it, we need to be simpler in the ways we configure the network, and we need to be faster. So today, the situation is we have SDV without SDN. We have a multiplication of network configuration for diagnostic, for debugging, for operation. So we need to deal with all this network configuration. In the future, we'll have more and more network configuration, and we would like to limit SDV. We would like to introduce SDN with what we call a limited SDN, which will be try to deal with this with a basic SDN controller and agent, and limited algorithms that deal of the swapping between network configuration. But this is tomorrow. In the future, we can imagine that we go faster to an advanced SDN controller agent. This is what we call SDV by SDN, where we'll have really optimized algorithms to run in embedded resources, and when the network configuration will really be done dynamic. But this is not for tomorrow, it's for the future. And we don't know when the future is. So we need to deal with the current problems. And the current problems is that today the applications QoS needs are given in proprietary format. So at the first step, we need that these QoS needs are standardized. In the future, we can imagine that these standards will be robust enough to support dynamic network configuration. Another thing we need to do better today is how we configure network device. Today we configure switches one by one. The rollbacks are not done globally, but also one by one. And the quality of service monitoring is really reduced. So tomorrow we need that we upgrade this configuration workflow, and we are willing to support the activities on Open Alliance TC9 to make things simpler. And this is what we see tomorrow, and tomorrow needs to be today very fast. And also, thanks to that, we will be able to do Ethernet backbone rollbacks centralized. And also, we'll have ways to monitor the QoS in a more standardized way than today. And in the future, for sure, we would like to extend that to the whole network, perhaps not to CAN or LIN, but to gateways. And this is part of what SDV by SDN goes, is really to control the network and be able to upgrade it much more faster than today. So yeah, the situation today is static config swap when we want to change from one configuration to the other. Perhaps when we introduce this new mechanism, the config swap can be done on runtime. And when we do SDV by SDN, it won't be not only a matter of swapping between configuration, but also a matter to calculate a new configuration on the fly. But as I say, this is the future. And today here, we are not for a revolution, as it was pointed yesterday. The revolution never meets its expectancies. This is an evolutionary approach I'm showing here, and I will showcase this with an example. Let's fly back to Paris. I suppose many of you have come from Paris for this event. And I know many of you know this big round square, which is the Arc of Triumph. It's a crazy place where if you have an accident, you are not covered by insurance. And there's a hell of a lot of accidents there, more than an accident every 7 minutes. And why so? There are 12 converging avenues, 70,000 vehicles per day. There's no lane marking. Traffic flows from every direction. And for ADAS, there are tens of targets to be computed. So I believe some people in the audience have taken this round square. Can you raise your hand, the people who has gone? And I believe everybody who has done this round square knows that is kind of a miracle if you don't have an accident. So this is worst case scenario for ADAS people, and you need to compute a lot of targets, as I said, and how all this is going to affect the networking. So we need to have extreme low latency, massive steps on data rate. So we just pointed out what would be a very simple use case. As we said, we need to gather the needs. So here we said we have a need of 10 to react in less than 10 milliseconds. And the sensor data we are gathering is 9 megabit per second. We have some resources, which is a 100 megabit backbone. So as we said today, the static situation is that we compute this information by simulation, and we find a situation where we are capable of answering to that. So in this simple example, we see that 90% of the latency budget of the system is taken by these needs. There's a lot of bandwidth left, 91% for other stuff, but not for latency. So what happens if we need to add new needs on top of that? So what we're going to answer? So first, the needs of this BC area design we have produced. And the good news is that this BC area design, it works only for quiet area design. But what happens if some marketing guys have a great idea and want to add a new function? Let's imagine that he want to introduce high-resolution augmented reality scenic view, a functionality that permits to put in the side windows information about the tourist hotspots in Paris. So this new information needs also a very low latency need, less than 10 milliseconds. It's not going to use as much data as before, only 2 megabits per second. But can we add this new requirement on top of the worst case scenario we had before? So what will happen if we use a static configuration? How to make everybody happy? So without SDN, what happened is that we add the two use case, and we see that 110% of the latency budget has been trespassed. So unfortunately, we go back to marketing people and say, sorry, your greatest idea cannot be done because we need to change all the network. There's not enough resources to answer to your idea. So what happens if we introduce the first step of SDN, the limited scope SDN? So the first thing that we'll need is kind of a mechanism of QoS monitoring that will look what is happening, where we are. We are in the quiet or busy area. And then we will need several pre-calculated network configuration, one for quiet area and other for busy area. So with simple arithmetics, we will be able to decide which network configuration we need to apply. If we are in a quiet area load, we will be able to apply this new functionality because only 60% of latency budget will be used. So the marketing people will be happy because we'll be able to deploy the new functionality without trespassing the the requirements. But what will happen if we enter in the Arc Triumph is we will get back to the worst case scenario, and the functionality will need to be deactivated, but because we cannot serve it. So this is to showcase a benefit that we might have if we deploy a limited SDN scenario. So I will hand the ball to Ricardo to say what we can do if we deploy the full picture of SDN.
All right. For presenting the first half of the slides. So I'm going to present the other half of the slides. My name is Ricardo Gonzalez, I work at Robert Bosch. I did those slides together with my colleague Florian Wagner. So I'm going to dig a little bit more in these SDV by SDN topics. So what I have as a first slide. So this is a little bit a recall how it looks like the state of the art when you design in-vehicle networks. As we can see in the picture, doesn't look so good. So what we have for hustles that we have to tackle as in-vehicle network engineers. So we have to handle heterogeneous networks. And this was presented yesterday by Schwarting in this story that she has to go from CAN to Ethernet, back to CAN, and was really challenged to meet the quality of service requirements. And this is my next point, quality of service requirements. Normally, we, in-vehicle networks engineers, we get some requirements, sometimes not so clear what exactly are the requirements. It's a challenge to design a system and you don't really know what you're supposed to do. The second point that was presented yesterday in the panel, they make the comment that in static networks, okay, you can have Excel, you put some numbers, magic happens, you get a configuration. But for, let's say, Ethernet-based in-vehicle networks with TSN and so, forget it. That's not going to work with Excel. And the last point, okay, we have a configuration. We want to deploy this configuration to the car. Comes the next problem. How to deploy these configurations to the switches, to the bridge devices. Every switch is slightly different parameters. Even though you want to deploy a configuration, maybe it doesn't work as expected. Another problem we have. All right, and why? We could use SDN to help us. So, before I talk about SDN, it's really important as an in-vehicle network designer point of view, we need to have some certain way to describe our system. So here I show the idea to have some kind of manifest. So what that would be, basically it's a way to describe metadata, configurations, and station information about resources, components, and services. So, for example, if you look in a systems engineering point of view, we can imagine we have a logical architecture that describes some function that has to send some data. And for that, we can imagine a manifest that shows the service level agreements. And this is really useful because later we can derive the quality of service requirements. Of course, we have to implement those functions. If you look more in a software engineering point of view, we can have a classic software components architecture. So basically, we show how those functions would be deployed in software as software components, and how it's going to look like those software interfaces. And then finally, all right, you have a piece of software we want to deploy to our vehicle. Then comes what I show here by the runtime architecture. So basically, it's our EE architecture elements, systems, communications, and so. And then, all right, we have application. Application wants to send some data. Quite common, we have certain level of a middleware. So that means it's responsible to pack the data from the application and see how to move this data forward. Of course, could be you have a data in another computer, so it has to go over your network layer. That's what I show by the TSN talkers and listeners. Here I talk about the traffic contract. In the next slide, I talk more about traffic contract, because that helps us a lot as in-vehicle network engineers. And then finally, we send this data over a network. And of course, I'm going to do the design of the network, so you need some way to describe those transfer delays and so that we can find our optimization. So takeaway, we can use the ideas like manifest to close the gap between what we as network engineers we need to know and what the other colleagues are doing, and then we can work together in the system. All right, so now going to the SDN part. I'm going to talk a little bit more about what Jose said before. So I'm going to show some building blocks for SDN, and slowly I'm going to build in a stepwise how we can introduce the building blocks from today and to the vision of the future, as Jose said. So first step, basically the picture of before, so that means a car without SDN. All right, I want to implement SDN. What would be the first step? So basically, we believe we need a way to describe your network systems there's no way to, why should we reinvent the wheel? We can use, for example, young data models. So basically, this is a formalization that describes your network in a hierarchical way. This is already used, state of the art for telecommunications. So why not reuse? It works. We can try to see how it would work for the automotive domain. Then if we have a way to describe our systems, we have the other point is the SDN agent. What the job of the agent? So basically is to make sure that we can deploy those configurations in the devices properly. Okay, we have a way to describe the system. We have an agent that helps us to deploy. But we need some way to send those configurations. And for that is the next building block. We need the SDN controller. So it's like a manager that's responsible to talk with the agents and send configurations. And for that, we can do it over the southbound interface. We can use, for example, netconf, coreconf, just for example, types of interfaces we can have. All right, so we have SDN controller, we can send configurations. But how I get to those configurations? We can imagine as a first step, we have, let's say, an off-board, I call here network engineering. So basically, we as engineers, we are sitting in our desk, we're running some simulations, running some optimization, find some configurations, and then we send over the engineering interface, the configurations, to SDN controller that over the southbound goes to the SDN agents. Okay, but we can think a little bit how that would look in the future, because here we have off-board, and then you send to the SDN controller. But what if we go one step further? All right, now the applications can ask directly what it needs over an SDN client. And for that, this last piece of the slide, we can do this over a northbound interface. So it's a, let's say, common channel that we can send. The application sends what it needs as a network resources point of view, and the SDN controller can be responsible to find those solutions. Okay, to finalize the slide, linking to the slide I said before, we as network engineers, we are looking mostly layer 2, communications and so, layer 1 and so. Of course, we have to look what I present here as the traffic contract. So I'm going to talk more about traffic contract in the next slides. So the idea is quite simple. We have a sender, we have a receiver. So the sender needs to send some data. We can have a common way to describe how this data looks like on the cable. So for example, we have what I call here the T-spec, traffic specification. And in the other side, we have the receiver. The receiver expects the data with a certain quality. Quality of service is always on the receiver side. And if you put together traffic specification and quality specification, we have what I call the traffic contract. All right, so takeaway. The usage of SDN, as I presented here, can be enabled to unleash SDV innovations. But I talk a lot about network. But now comes the point. What about the computation side? Because in order to derive the traffic contracts, somehow I have to understand what application needs to send over the cables. And now comes the other slide I have to present. So a common scenario, we have either a new application or you want to update the application. You can run some optimization to find the usage of resources, either computation or network, and deploy to the car. Okay, how we can link this connection between the computation resources and network resources. So this is basically the picture we had before. We can imagine from the TSN talker, SDN listener, so this is really close to the SDN controller side, so we are making the resource management on the network side. But if you want to get the needs from the application, if you look logically, okay, the first step we have in between application and the TSN talker listeners is the middleware, and here we can see probably the middleware could be responsible to make this connection between the application's service level agreements and the traffic contracts that we need to send over the network. And finally, this is a little bit extension of the talk. Okay, we talk about networks, SDN, but I could imagine from the software point of view, like a SDV manager, something like this, that, okay, you have a new application and it has to talk to my SDN controller, what type of traffic contracts I need, and maybe they can even try to find agreement between them to use the resources in an optimum way. And this is the takeaway for this slide. We need a proper connection between network and computation resources management to be able to achieve the determinisms in a more dynamic development cycle. All right, good. So these last 3 slides was a lot of information. For the next 2 slides I have to finish my talk, together with Jose, we did like a use case example using the scenario that he said about the Arc de Triomphe and so. I'm going to present. What we have for the architecture. So basically the architecture, we have a vehicle computer, a head unit. and some edge components. So we have the smart camera, smart radar, telecommunications unit, front display, and smart window. The smart window is the scenic view that he commented, that you're driving around the city and show some information on the screen. And everything is connected over 100 base T1S. Sorry, 100 base T1. Okay, now linking to what I presented, we have some applications running the network. So what could look like an application manifest. So I'm going to use the same scenarios as Jose presented. So we have the quiet scenario and the busy scenario in green and in purple. So from the application point of view, okay, different scenarios, I have different needs, as we can see here on those parameters. And we have a different amount of data as well to be sent. The cycle time is the same, but the amount of data to be sent is different. But me, as an in-vehicle network engineer, this doesn't help much, because I don't know exactly how this data looks like on the cable. And then comes the part more related to us. We can imagine that from this application manifest, we can derive a traffic specification, quality specification, shows how the data would look like. So stuff that first matters, like the burst size, the average rate, the senders, the receivers in the network. And quite important as well, that in the next slide is going to stress more, we have the Q spec that says how looks like the expectations for this data. So in case we have a latency that is smaller than the value of the cycle time, you can see that the expected rate has a different number than the average. This I'm going to stress more in the next slide, but it's a really useful information for us. And just for completion, in order to do the simulation to play around for the optimization, we added all these other traffics as well, just for the completion of the example. All right? So what is the analysis for this use case we have? OK, so we build the network, we run the applications, and we run the scenario with the quiet area. For the example of today, I'm going to stress in this link between the vehicle computer and the head unit, because this is like the bottleneck on my network, and this is a really point of interest that I can try to find optimization for the network. In this scenario, I play basically with priorities and shaping. So in the quiet area, using the T-spec and the Q-spec, so basically the average number was 42 megabits per second, so below the 100 megabits per second. This is the sum of all the traffic going this link, in this direction, to be precise. Interesting, the expected rate that comes from the latency requirement, it's slightly bigger, but still below the 100 megabits per second. So with the optimization, we're able to find a solution. All good. Now, let's say you just got your car, and then you got inside the Arc de Triomphe. Chaos. Your smart camera is detecting way more objects, and now the amount of data to be sent over the link. The average doesn't change too much, but the important point is the expected rate, it's above the 100 megabits per second. What that means? No chance to find a configuration that fits the latency requirements. And now comes a little bit to what I present in the talk. Okay, we have a network. The network is fixed. It's not like we can change the speed of the link. So what we can do in the network point of view to try to use the resources available to find a solution. So then we play the idea, okay, you got in this specific scenario, we have a lot of objects, and we still have your kid in the back watching this scenic view in 4K. What if maybe we degrade a little bit the scenic view, so we don't set the full resolution, maybe we set less resolution for that, and because of this, it's like a negotiation. Okay, I need more data from this application, another application needs to give, and then we give the scenic view, because the scenic view is more like a gimmick, and the ADAS is more safety critical, so we should give more room for this application. And after this negotiation, then we reach this 87 megabits per second. That's below the 100 megabits per second of the link, and are able to find a configuration that works. And that's the takeaway. So the idea is we have this SDN manager, SDN manager, SDV manager. Maybe they work together, they find agreement, and then we can find a solution that works in our resources that we have.
The conclusion.
I do now the conclusion to finalize my slides. So, final slide for me and Jose of today. So we talk a little bit about SDN, introduced by steps, where I show the building blocks. We talk about this manifest harmonization. So we need to have a common way to describe our systems, for example, Young models and so. And as well, talking about Young, we have this network management foundation. Still, we have work to do. Of course, this is vision, how we want to reach. We still need to refine how to introduce SDN in a stepwise. So no moonshot here, but how to do step by step. We need more collaboration between, let's say, the software side and the network side, that we can derive properly the usage of resources. And finally, to link with TC19, we are already working today to try to standardize the way to describe the switches and bridge devices. And that's it. So with a proper interface and methods, SDN can unleash the full potential of SDV. So please, just if you want to discuss a little bit more, just talk with me, Jose. We are more than happy to discuss. Thank you.
So thank you, Jose. Thank you, Ricardo. That left us a few minutes for 1 or 2 questions. So depending also for the answers. So please feel free.
Thank you for the great presentation. As a standards guy, my question is what you really want to standardize. And the reason I'm asking is because, as you said, many of these things are done, like for the telecom network. So practically speaking, SDN is 3 principles. Separation of the control plane from the data plane. So instead of running fully distributed protocols, you have the SDN controller, as you said. And the SDN agent, as it turned out as of today, is just a YANG. So, I mean, on the device, you have a device exposed by a YANG. So there is no specific agent other than handling the managed object that are very standardized, exposing it in YANG, and you have the SDN controller. The SDN controller in TSN terms is called Central Network Controller. I haven't heard that one in here, and many people did not want to standardize the algorithms of the CNC. Some features, I mean, a CNC being compliant to an industrial profile like IEEE 60802 is specified, like topology discovery and stuff is needed. And the interface between the CNC and there is a CUC that knows about the application stuff. What you said, QoS monitoring is called operation administration and maintenance. There are standards for that in Ethernet. And what is, I heard also recently at the TSNA, the traffic specification. So I would understand if you would like to have finer granularity compared to the existing standards. But I'm not sure what you want to standardize compared to the given standards.
Very short answer. We want to do a stepwise standardization, and it will start with Open Alliance TC19 activities. And I don't know if you were in Open Alliance meeting TC19 on Tuesday, and invite you to work in these activities is really start by the network configuration of the switches. With a data model, we are not talking about TSN, we are talking about how to configure the switches in a standardized way, because today there are different SDKs by different tier 2, and we want to have a unified way to give the configuration to be able to switch from one switch to the other. TSN will come in a secondary step, and the controller, the agent, the ESDN concept will come later. But we need to start with step 0. If we go to step 0, I think they are going to come with SDV more and more use cases, more and more requirements. And if the use cases are there, for sure we'll look what is being done in telecom industry, as we always do in automotive. But you know, telecom industry sometimes have infinite resources, have very few resources. We need to do things simpler, cheaper, and to be able to run with very few resources in cars. So.
And nobody has infinite resources, but maybe I would suggest also take a look at the aerospace profile, because they chose to go this way at the end, and they have the very same problem on how do you get it into the EEPROM, which is not so standardized, and the profile gives guidance on that.
Okay.
And I would
definitely look into that. Thanks for your advice.
And I would be happy to contribute to TC19, but I don't have access. So.
Thank you. Thank you again, Jose and Ricardo. So now